Okay, so here's a very cool construction. I'm taking a regular pentagon ABCDE, centered, whose centroid is a point O, and then I'm taking a point P, which is going to glide along some circle centered on O with some specified radius. Okay, I can control the radius here, but let me get to the construction first. So you can see that P is gliding along some circle centered on the centroid of the regular pentagon. Now I'm going to take 5 subtriangles. Let's just show the first one. For every side of the pentagon, I'm going to compute a triangle PAB, so this brown triangle here, and then get a triangle center off of this triangle, in this case x2. Okay, and I'm going to do the same for PBC and get its x2, which is this point here, and then do the same for the next side PCD and get this x2, and so forth and so on. Okay, so now I get 5 x sub k's, k in this case is 2, so I'm computing the barycenters. And what I'm showing here is the conic, this purple thing, that passes through these 5 xk's. Okay, so the first thing that you realize is that if the xk that you're computing is the barycenter, those 5 points are concyclic, i.e. the conic is a circle. Okay, for whichever position of P. Now, as P traverses a circle centered on O, the center of this circle is going to sweep this orange circle, concentric with the outer circle. Okay, now, if I, for example, if I change the radius of this locus of P, let's just change it. You can see here that I get a different result. So now if P is moving along this smaller circle, I still get 5 points that lie on a circle, 5 x2s that lie on a circle, and the center still follows a circle. For the special case where the path of P is this internally tangent circle, you got a specially harmonious situation where your circle it passes through P itself, and the locus of its center is another circle that is tangent to, the conic will be tangent to the locus of the center, right? So if I animate P, for example, you can see that. All right, so you have 5 x2s that are concyclic. All right, and just to show this, let's say this position here, okay, when the locus of P is a circumcircle of the pentagon, you don't get anything special as far as I can tell. Perhaps there's an interesting radius here that you're obtaining for the locus of the center of these purple circles. Okay, but what I actually want to show you is what happens when instead of computing x3, you compute, sorry, instead of computing x2, the barycenter, you compute x3, the circumcenter. Okay, now let me vary R a little bit so we don't get a situation of instability, which happens when P is moving along the circumcircle. Now this case here is fantastic in my opinion. Now let's just recap what we're doing. I'm taking a point P, which is currently in some location in a circle of some controlled radius R. Then I'm computing 5 triangles, PAB, PBC, PCD, PDE, and PEA. And for each one of these triangles, I'm calculating its circumcenter, x3. Right, so for this case here, I'll be drawing a circle that goes around PAB and computing its center. Now it's over here. Here's the x3 of the first triangle in brown, okay? Now the other points on this diagram are the other x3s of the other subtriangles. Now if I get 5 points, I can always draw a conic through 5 points. Now something really magical happens here. The conic that goes through these 5 points can be an ellipse, or for larger radii of P here, it's going to be a hyperbola, okay? But what's really amazing about this is that over the family, one of the foci of this conic is the center, is the centroid of the pentagon. And the other focus is moving along this green circle. Now what you see here is that This is actually a rigidly rotating ellipse. Okay, I'm showing here its eccentricity so you can see that it does not change over the family. So this is a rigidly rotating ellipse with one focus automatically falling upon the centroid of the pentagon. I found this to be quite interesting. Maybe this is known, maybe this is trivial. I certainly haven't seen this before. So if I change, for example, the radius of the P circle, right? Let's make this radius of P circle be, yeah, so there's an interesting radius for the P circle, okay, where the center of the conic is on P. So that's that orange curve. So there's a radius for the locus of P, for which the center of the conic is exactly P. Now, if we keep increasing that radius, okay, you can see that I still have an ellipse, but at some point, oh yeah, let's do this case here. This case is fantastic as well. When the locus of P is the circle which is internally tangent to the pentagon, regular pentagon, you can see here that the eccentricity of this thing is locked at 1, meaning that these guys are parabola. So you get this really cute result here as well, right? So you're getting a family of parabolas, and one of the foci of this parabola is the centroid. You can see here that it's quite asymmetric, right? The 5 points that I'm computing, they don't have any visible symmetry, but yet, if you pass a conic through them, you end up getting a parabola. Right, you can see here that there is no point that, is collinear with, PO, okay, but yet you're getting this parabola. So this is kind of like a limit case. Now if I keep expanding R, you come away from the parabola, and now you're circling back to a related family, which is that of hyperbolae. So you can see here that my eccentricity is greater than 1 now. So it's a hyperbola. And you have one of the foci of this family of hyperbola still at the centroid O, and the other focus is moving along a circle. Okay, so if I keep increasing the radius, I'm going to get a family of hyperbolae, right? Until I hit a crucial location, which is when this guy here becomes the circumradius. Sorry, the circumcircle of the pentagon. In which case my hyperbola degenerate to 2 straight lines. I'm pretty close to that situation right now, which means that both the foci and its center are going to converge to O. Okay? At the location when R is exactly equal to the circumradius, GeoGebra blows up. Okay? That's fine. That's fine. Let GeoGebra blow up, because I'm just getting a family of degenerate 5-point conics. Okay? Now if I keep increasing, okay, I go back to the hyperbolic case as such. One fixed focus, fixed eccentricity, so these are rigidly rotating hyperbolae. Okay, so much for this case. Let's go back now to the orthocenter case. Let's now investigate the orthocenter case, k equals 4. Now you look at this and it's like, okay, the locus of my P is too big. So I'm getting a very confusing high degree set of curves here for both the locus of the center and the locus of the foci. But let's go back to the simple situation where things seem to get organized, which is when P, can I do that? P is actually moving along the circumcircle. Now what am I getting here? I go back to the situation where my 5 orthocenters are concyclic. Furthermore, the center of the circle that passes through these 5 points is P itself. Perhaps this is obvious, but I had not seen this construction before. This is an interesting interplay between, if you think of regular n-gons as complex roots of unity, right? It's an interplay between the algebra of the complex roots of unity with the algebra of orthocenters. Okay, so maybe in the complex world, the proof to this phenomenon here would be an easy one. But I want to show you a very interesting thing. I'm going to perturb the radius of the circle upon which P is gliding just by an iota. So let's go up a little bit. I'm going to go up an iota. When I go up an iota, everything explodes. Okay, so now P, you can see here that P is going just... okay, this is going to struggle because this locus is pretty ugly. So let me go back to... So, I perturbed it up. Let's perturb it down now. I also get a very complicated path for both the center and the foci, okay? So if I keep going down on R, I can tame this mess for X4. So for example, so when P is moving along a very small circle, you tame the mass of the locus of the center of these conics and the locus of their foci. Now as I keep increasing my P radius, you can see here that locus of these two entities starts becoming more spiky. At some point you're going to go through infinity, which we've already crossed that threshold. Not that this is important in any way, but you can see here that we're dealing with loci which are algebraically quite complex. They're probably at least of order 10, of degree 10, right? Could be higher than that. So you can see here that you get this whole full-fledged set of morphologies for, I don't want to use the word topology, but morphologies for the loci of X4, the very humble X4, the orthocenter, right? And it's only until you hit, so it's only at this particular setting that you get an organized or singular locus. At the situation where P is moving along a circle that is internally tangent, there's nothing special, okay? Now let's move forward here to a couple more observations. If I can stop that. Let's go to x equals 5. Okay, so x equals 5 is pretty disorganized as well, but if I make P flow along the circumcircle, I get an organized set of circles with their center constant radius, right, and their center moving along a circle. For x6, so x5 is the center of the Euler circle. x6 is the symmedian point. For small enough, actually x6 is always well behaved. Even if I move R, you can get complicated morphologies here, such as this one for certain radii. Okay, but it's fairly well behaved. I don't think it ever spikes out. It doesn't spike out. You can see that, okay? But there's nothing really interesting. Maybe you can say, this thing is graphically interesting. Let's move on to x7, pretty complex as well. I think this one does explode. So green is the more complicated path of the foci, right? Look at that. This is geometrically beautiful. Okay, this one is well behaved. It doesn't seem to explode. The Jargon point, right? Doesn't want to explode. Okay, fine. How about x8, the Nagel point? Nagel point, if I remember correctly, does explode. Let's see. So I start with a very small radius for the locus of P. Keep going up. Yeah, it's going to explode. So it explodes here. At R equals R, doesn't have anything. R equals big R, right? The circumradius. Doesn't do anything particularly interesting. When the circle is internal, it does this graphically beautiful set of loci. Okay, and I could keep going on, x equals 9, equals 10, but I want to show you x equals 20, which gave me a pleasing result as well. And this is a consequence, perhaps, of what's going on with x3 and x4. I believe x20 is a reflection of, I think, x4 on x3. So when r is internal, when, you know, the circle is internally tangent, it's disorganized. But when r equals big R, you get an organized situation. And very similar to the x4 case, right? Except that now the center of my circle is diametrically opposite to P. So that's x20 for you. For a small radius, it disorganizes. For internally tangent, it disorganizes. What if I go up a bit? It also disorganizes. You're going to get some crazy geometry here. Okay, so I think the highlight of this discussion, thankfully, are the low index. I never showed you guys what x1, the in-center, does, because the in-center is somewhat nonlinear. Here it is, right? So it's basically giving me regularized versions, okay, of the regular pentagon, both for the locus of the center and the locus of the foci. It looks like one of the foci is pretty close to O, you can see here, right? And the other one is going through this regular version of a pentagon. If I increase the radius here, well, if I decrease the radius, I can get different shapes, basically betraying the fact that these curves are have a quite high degree, okay, even though they may hide it, okay. But there doesn't seem to be anything particularly interesting with x1, okay. But with x2, just to recap the highlights, with x2, I get the circle, conic, set of conics, with a special case of when I'm internally tangent, so P is moving along a circle that is internally tangent to the pentagon, I get the special case. The conics are always tangent to the locus. And then for x3, which is my favorite, except for this, okay, for this case I get a parabola, a set of parabolas. For when r is external on the circumcircle, you get a set of degenerate right angle, no, not necessarily right angle, but you get a set of degenerate, let me just jog this a little bit forward here. Yeah, you get a set of degenerate hyperbolas, so basically the union of two lines, right? But for any other case, for example here, you get this beautiful result, which is the set of conics passing through the 5 x3s of P with the sides of the pentagon have a fixed focus on O, okay? If I reduce that, I get an ellipse here. So if my R is over here, I get an ellipse. So you have these three cases, right? You have a set of ellipses. If the radius of the motion of the locus of P is less than the internally tangent one, which at this point you get a set of parabolas. And then if you're bigger than the circumradius, you get a set of hyperbolae. Okay? All right. Well, so much for this video today, and I'll see you on the next time. Hopefully with having gotten healed from a terrible cold that I've been struggling with for the past week. See you in the next video.